Hello class, it's Ms. Augustine. I was reading some of your journals and see that you're struggling still with the worksheet about energy calculations. So I put together this little presentation, Understanding Light and Energy, and we're going to give it a whirl. So first of all, we were talking about light and atomic spectra, and we said that according to the wave model, light consists of electromagnetic waves, and that the height of the wave is called its amplitude. And again, according to this wave model of light, we have this diagram. So amplitude is the height of the wave. A wavelength is the distance from crest to crest. So it's the measurement, it's a length measurement, and it's a measurement of the entire length of a wave. So again, from crest to crest. And then the other thing we talked about is the frequency. And so if you picked a point and then you said how many complete wavelengths pass a point per unit time, that's what we call the frequency, and that's measured in wavelengths or cycles per second. So its unit is actually inverse seconds, 1/seconds, and it's called a hertz. So when we're talking about electromagnetic radiation, we're talking about the form of energy that exhibits these wave-like behaviors traveling through space. Again, the electromagnetic spectrum includes all of the different forms of energy that exhibit these wave-like properties. So it's all of the wavelengths of light in our universe. And again, the speed is a constant, and the speed of all electromagnetic radiation in our universe is a constant, and that number is 3 × 10⁸ meters per second. So we use the unit, or the variable c, to express the speed of light, and again, light referring to all wave-like electromagnetic radiation, and it's 3 × 10⁸ meters per second. So again, if we're talking about all of the electromagnetic radiation in our universe, it goes everywhere from gamma rays, which are the highest energy and the shortest wavelength, through to shortwave and AM radio, and again, those are very long wavelengths, 10⁴ meters. And we said that this little tiny slice in the center is visible light, light that we can see. So what that means is if I'm seeing light that is red, then it is in this region here, which is probably 800 to, I don't know, like 690 nanometers in length. And again, if it's in that particular region, our eye sees it as red. If light is, for instance, around 600 or 570-ish, then our eyes would perceive it as yellow. On down to 400 nanometers, we see it as violet. So remembering that with the wave model of light, we can calculate the speed of light is equal to wavelength times frequency. So there's an inverse relationship between wavelength and frequency. The longer the wavelength, the shorter the frequency. The greater the frequency, the shorter the wavelength, because this times this is a constant. So when one goes up, the other has to go down. And again, c, the speed of light in meters per second, is a constant. So there are our variables. So what that means is that we can calculate. If I know the wavelength, I can calculate the frequency because c is constant. If I know the frequency, I can calculate the wavelength because c is constant. And again, c is 3 × 10⁸ meters per second. So remember also that the particle description of light, which was forwarded by Max Planck, proposed that energy exists and objects emit energy in these small discrete packets that he called quanta of light. So singular would be a quantum of energy, and that's that minimum quantity of energy that can be lost or gained by an atom. So the equation that we use to express the energy for a photon of light. And remember, we said that light behaves as both a wave and a particle. So if we want to calculate the energy of just a particle of light, even though it's behaving like a wave and moving through the universe, we can also treat it like a particle. And in that case, if we wanted to calculate the energy of just one particle, one photon, one quantum, so to speak, of light, it's using this equation. The energy E is equal to this constant, Planck's constant, times its frequency. So that worksheet that you were doing is allowing you to calculate the energy if you know the frequency, and you can get the frequency if you know the wavelength. So you can measure the wavelength, calculate the frequency, and then use the frequency to calculate the energy of that particular photon. And energy, again, is directly proportional to the frequency, and energy, our unit is joules. Now you might say, joules, that sounds vaguely familiar. Well, energy in joules was what we were calculating also when we were doing our heat calculations, and we're talking about energy in terms of heat, and we were using our Q equals M times C times delta T. In those cases, the energy that we were calculating, and for heat energy, we were using the variable Q, you'll recall, our energies were often in kilojoules, so we were calculating the amounts of energy to raise the temperature of water. And in those cases, it was 1,000 joules or 10,000 joules. In this case, since we're measuring the energy of just a little photon of light, that's why our calculations are coming up with numbers of 10 to the minus 19th joules. Because if you think about it, you're talking about a really tiny particle of energy associated with a photon of light. And then Planck's constant has the unit joules times seconds, and our frequency, we said, is a hertz, which is the same as an inverse second, or 1 over a second. So let's try another one of these calculations. So in this case, again, we're still using our c, with the c being the speed of light, lambda, this funny little Greek symbol, is wavelength, and nu is our frequency, and our speed of light is always 3 times 10 to the 8th meters per second. And again, we're remembering here our energy is E, H is Planck's constant, and frequency is the Greek letter nu. So in this case, let's calculate frequency. What is the frequency of light with a wavelength of 310 nanometers? So there's our equation. Remember that 310 nanometers is the same as 310 times 10 to the minus 9 meters. And when you plug that into your calculator, it turns it into correct scientific notation, which would be 3.10, 3 sig figs here, times 10 to the minus 7 meters. So then we're going to plug in our numbers. So here, rearranging, frequency is c divided by wavelength. Plug in c, plug in our wavelength, and we get 9.68 times 10 to the 14th inverse seconds. Remember, in this visible region, our frequency is typically going to come around 10 to the 14th inverse seconds. So now I want to calculate the energy for that same wavelength of light that we just determined the frequency to be 9.68 times 10 to the 14th seconds minus 1. So again, there's our equation. Here is our frequency. Here's Planck's constant, and then we plug in E is equal to Planck's constant times that particular frequency, and we'll get an E equal to 6.42 times 10 to the minus 19th joules. So now you're ready to try more of these energy practice problems, and I'm hoping that this tutorial helped you a little bit. Ms. Augustine signing out.